Hello everyone and welcome to a new episode of Golang Cafe, and today we are going to talk about Mutex in Go. In one of the previous episodes we have seen how we use goroutines and channels to make our program faster by using concurrency. We have seen also how we can synchronize different goroutines together, for example using wait groups and using channels by sending data across different goroutines. We haven't explored yet one of the concurrency primitives, or at least one of the ways that we are going to use when sharing a resource between different goroutines, which is the mutex. The mutex is a way to synchronize access to a shared resource. So it's a very specific scenario, and you will be able to understand where you need to use a mutex very easily, because the scenarios where you use a mutex are pretty straightforward. It's when you want synchronized access to a shared resource, and when effectively you are doing some sequential access to a variable or to a resource. In our case, it's going to be a cache. So the cache that we have today is just a struct that contains a map. It's a key value store in our case, so it's a string to integer value, and it's just an in-memory cache, as you can see here. And we are into our program, we are creating 100 random keys. We are saving. I call this a save slow because it's not using goroutines now, it's just using playing Go without goroutines, and it's just saving the key and the value into our cache, as you can see here. It's pretty basic. Then we have the save with the goroutine, which we are going to see later on, and it's using a wait group, so it just tells us when it's finished with the wait group.done. We are saving 100 random keys, and then we are printing the value of the map. And we are going to first run this without goroutines, then we are going to introduce goroutines, and we're going to see why we need the mutex and how mutex work in our case. So we can just run our example. This is going to load 100 random keys in our map, as you can see here, user ID and random ID and then random number. And now we just want to make this concurrent, and the way that we can make this concurrent is very easy. We can just use the go keyword, specify the save, and then specify the wait group that we want to wait for 100 goroutines. This is something that we've seen already in one of the previous episodes about wait groups, and I can add the link in the description below so you can refresh on that, but it's pretty basic. So we are just telling the main goroutine to wait for 100 goroutines. And all the goroutines will then tell the wait group that they have done just at the end, and this will effectively speed up our creation of the cache, our populating the cache. It will speed up in a very efficient way because we are spinning up 100 goroutines in this case. So let's just try it out. Let's just run it again like we did before. And we will see that we get some errors. So the errors we are gonna get, it's pretty straightforward. The first error is concurrent map writes, and it also tells us where we are doing concurrent map writes. Line 29 it tells, at least at the beginning of our stack trace. So concurrent map writes is effectively what you want to avoid by using mutexes. It's not just for maps, bear in mind, also for when you have, for example, any other variable, for example integers or strings, global variables being accessed by different goroutines, so you want to synchronize the access to those. And the way that you synchronize access to those is by using the mutex. The mutex is in go doc sync.Mutex, so it's in the sync package which we already imported. And the mutex is a mutual exclusion lock. That's just the shorthand for the actual meaning of the mutex. Mutex stands for mutual exclusion lock. So the zero value for a mutex is unlocked mutex. The only thing that you need to bear in mind about the mutex is that you can have two states. The mutex can be either locked or unlocked, and the state of the mutex can be known by all the goroutines. So it takes care of having this global state that is accessible by all goroutines. So if one goroutine locks the mutex and immediately after another goroutine go and check the mutex, then the two goroutines will see the same value for that mutex. And that's why it's used for synchronization. Generally speaking, when you lock a mutex, nobody else can lock the mutex. It means that you can only work with the mutex. When you unlock the mutex, you release the mutex, and all the other goroutines can then lock the mutex and use the mutex. And you can also see that by looking at the documentation. You see lock, which is the function call, locks m, which is the mutex. If the lock is already in use, the calling goroutine blocks until the mutex is available. So let's say that you have a goroutine A that first goes into the mutex, calls the lock method, and then there is a goroutine B which tries to lock the mutant again while the goroutine A is still working on the operation, still having the mutex in a lock state. Then the goroutine B will block. It will block until the goroutine A calls unlock into from the mutex. So the unlock releases the status of lock from the mutex for a given goroutine and will effectively allow other goroutines to lock the mutex and take that state of locking so that they can work without clashing with other goroutines. And that's why we usually use the mutex. So in our case, we're just gonna do mutex sync.Mutex. So we integrate the mutex within our struct, and the way that then we use the mutex, before we write into the cache, we are going to require a lock. We're going to acquire the lock. In memory cache .mutex.lock. So at this point, no other goroutine can lock the mutex. So if there is another goroutine that initializes, that arrives here and initializes this function and tries to lock the mutex, it will be stuck here, line 30, until the other instance unlocks the mutex. So we also need to unlock once we have written into the cache. So mutex unlock. This will release the lock and will allow other goroutines to write into the mutex. And that's effectively what you need in order to write to a concurrent, to a shared data resource between different concurrent goroutines. So now we can just run this program again, run main.go, and we see that we don't have the issue anymore. So in terms of checking if you have any race condition, you can also check run -race main.go, and this will allow us to spot in advance certain issues in terms of data races. We're gonna see in another episode more specifically how we can use the race condition and how we can improve that. In terms of mutexes, there is also another type of mutex, which is sync.RWMutex, which is a read-write mutex. And the read-write mutex, the only difference is that with the standard mutex, whenever there is a lock event, nobody can read from the mutex, and nobody can write from the mutex either. From the read-write mutex perspective, there can be more than one reader at the same time. So if there is a read lock, there can be more than one read lock. There is only just one lock. The read lock allows us to read from the mutex, so it's intended as a read operation from the mutex. It doesn't change the data. In terms of writing, if there is a one lock operation, still there cannot be more than one writer at a time. So effectively, the difference is that with read-write mutex, you have one or more concurrent readers and only one writer. Okay, that's effectively the read-write mutex. And with the standard mutex, you have only one reader and only one writer. Why is this important? This is important because whenever you want to implement a mutex and there is a slightly different behavior in terms of read and writes, you can implement that and bake that into your mutex. For example, in our case, we are mostly writing into the mutex. We are not reading into we are mostly writing into the mutex. We are writing into the cache. We are not reading from the cache. So we don't have concurrent reads. But if we had concurrent reads, we could do read-write mutex. So whenever we save, we do a write lock, so there can only be one writer at a time. But if we were to have, for example, let's say at the same time we have 100 readers, then the optimization could lie in the fact that we can have more than one reader, and we can do that by doing, for example, go func. We have a goroutine here. and then we can do, for example, in memory cache. .mutex. This is a read operation. It doesn't change the value of the mutex, and so there can be more than one goroutine reading at the same time from a mutex point of view, and so you can do read lock. The read lock will succeed even if there is another read lock open, but will not succeed if there is a write lock open. So there can be more than one reader, and that's useful when, for example, you have imbalance between the number of reads and number of writes. For example, if you have a lot of reads and a few writes, then if you implement in a cache of this type, you want to make sure that you have a difference between read lock and write lock. Because if you have a lot of write lock, you create a lot of contention in your map, so you will create a lot of waiting. A lot of the readers will wait so that they will wait so that all the goroutines have access the value just one at a time. But in case of reading, we know that the value is not changing in the mutex, so we are safe to read all at the same time. We don't mind if there are other goroutines reading. And so in this case, we're just going to do a print, a dump of our in-memory cache and m. And then we do effectively the in-memory cache mutex unlock. I'm not sure if sync read write mutex, it's read unlock, so make sure that you do read unlock and not unlock, so it's reflected to what the lock has been requested. So if you lock for a read, you should unlock for a read, and if you lock for a write, you should unlock for a write. And that's pretty much it. So now we can also add the wait groups. Wait groups.add, make sure that we have the right amount of wait groups here. We also do wait group.done, and that should be pretty much the same. Let's see, read unlock. This is with the uppercase. So you can see here that we have been reading from the map 100 times without any issue whatsoever. And this is effectively how you use the read and write lock from a map. So the takeaways are when you are reading from a map, you can use, when you're reading from a shared resource in general, it's not just a map. When you're reading from a shared resource, you can use the read lock, so it doesn't create contention with the data structure that you're sharing. In terms of writing, you will need to use the write lock, as you can see here. So it's useful to have a read write mutex when there is a difference in behavior. If the behavior is always a write, for example, as it was before, you could just use the standard mutex. And the general scenario is effectively as simple as that. Locking the mutex, using your resource, and then unlocking the mutex. That's exactly how it is. It's just guarding every access with the mutex. Also, something that we haven't done is guarding the access to this cache. Also, when we read just at the end, we know that there is no other goroutines running, but this is something that we know because we know that our code it's structured in this way. But it's always a good practice also here to guard this shared resource with a lock and an unlock. So in this case, it's fine because we know that there are no other goroutines going on. So we wait for all the goroutines to finish. We know that there is no other operation going on. And so we don't need to lock and unlock the mutex to read from the map. But in this case, this is effectively what's happening. So this is the readers. We use the read unlock, read lock, read unlock. The writers use only the write lock. And that's the mutex. So it allows us to write to a shared resource by using goroutines and by allowing us to control sequential access to a shared resource in Go. I hope you liked the tutorial, and see you in the next one. Thanks for watching.